Okay, let's start Team 1's presentation. Before we proceed with the production, our group prepared the checklist by dividing the process into 3 parts: upper window mask, metal mask, and backside mask. Because our processes cannot be complete within a day. And based on this, we proceeded with the process. Next, I'll give you a brief explanation of the reason for choosing the process conditions. We will proceed with each process. Silicon oxidation is the process where oxygen reaches the silicon surface in a hot furnace and forms silicon oxide. During this process, oxygen diffuses through the oxide layer and reacts with silicon, consuming it. As the reaction proceeds, the boundary between silicon and silicon oxide moves toward the silicon. An important point is that the silicon oxide boundary is located at about 44% of the oxide thickness as the oxide grows, meaning silicon is gradually consumed as oxidation progresses. After cleaning the wafer using piranha solution, the process was followed. After that, the process of oxidizing the wafer for the first time took place through the above step. You can check the surface condition of the wafer after the oxidation process through the photo during the process and the result photo on the right. Silicon wafers are initially hydrophilic. This is because the OH covalent bonds are present on the wafer surface, which make them stick to water well and have a lower contact angle. However, when HMDS is used to treat the surface, a non-polar bond called CH is formed on the surface, which makes the wafer surface hydrophobic. This hydrophobic surface does not adhere well to polar liquids such as water, so it can bind well to hydrophobic materials such as PR photoresist. This process plays an important role in increasing the adhesion of PR. Additionally, the HMDS application method was uniformly applied to the silicon wafer using the spin coating method and then baked at 120 degrees for 60 seconds to blow away the non-applied part. This ensured that HMDS adheres well to the wafer surface and then PR application can proceed smoothly. As the concentration of the TMAH solution decreases, the etching rate increases. In other words, the lower the concentration, the faster the etching proceeds. However, it is also important that the lower concentration, the more rapidly the surface roughness deteriorates. As the temperature rises, the etch rate increases even at the same concentration. In other words, it should also be taken into account that the etching proceeds faster at higher temperature, which can result in poor surface quality for reasons such as undercut phenomena. Hillock was formed on the surface at low TMAH concentration, but the surface uniformity improved as the concentration increased to 20 weight% and 25 weight%. In addition, As the temperature increased, the etching rate increased, but the etching selectivity of silicon and silicon oxide could decrease above 80 degrees. Therefore, it can be seen that proper adjustment of the TMAH concentration and temperature is important for uniform etching and maintaining selectivity. By combining this experimental result, TMAH concentration of 25 weight% and TMAH temperature of 80 degrees were set as optimal conditions. It was determined that this condition could satisfy the etching rate and surface quality at the same time. The image below is the image that we sent the mask file that we produced using the program to the mask production company. The image above is the image of the actual film mask that was produced by the production company and delivered to us. Before going into the process, we will use an optical microscope to make sure that it is accurately produced as intended. Through this, we plan to finally verify that the actual mask is made according to the requirements and then start the process. Thank you for your attention.